I'll time this. Or can somebody tell me when I'm at 45 minutes? And then, okay. Thank you, Duncan. To have you introduce me is, it's like if you went to the Rolling Stones and the Rolling Stones introduced like Barney Bentall or something like that. It's like, I appreciate that. And thank you for coming out to learn a little bit more about our debris flow barriers. And I appreciate your interest, and I know everybody's busy, and thank you, Tyler, for giving me a chance to share a little bit about what we do. I'm more of a rockfall attenuator guy, but I do kind of dabble in these debris flow barriers. I find them quite fascinating. And I've been working for Geoberg in Canada for 12 years now, and I didn't sell medical instruments before, like Mr. Toman did, so bit of a geotech background. I know some faces in here. So anyways, debris flow mitigation with flexible net systems. So the agenda today is I'll talk a little bit about the debris flow process, share about our research and our dimensioning concept, and some of our systems and our case studies. Can everybody hear me okay? Is it pretty good? Okay. A little bit about the process. So there's people in this room that definitely know more about this than I do from a theoretical point of view. So I won't get too far into the weeds on this one, but the decisive factors are rainfall and debris. So basically, something has to be mobilized, something has to move. This can be loose debris, gravel, sediments, woody debris, ash. When you combine that with rainfall, we get these debris flows. And just in my time with Geoberg, it seems like these rain showers are more intense and more frequent, and after wildfires it seems to be the perfect mix to create these debris flows. And all of you have probably seen a picture like this in your studies and notes, but some of the triggering effects for debris flows obviously are steep slopes, so we're blessed with those in British Columbia. Frequent rainstorms, heavy rains, intense rains, melting snow, saturated soil, dealing a lot with weak or loose rock and soil, weathering, erosion. Wildfires, a new one I put into this slide because most of the barriers that we're putting in now are because of wildfires. Changes in surface or subsurface runoff patterns, geometry changes from construction or grading. So we all have been out in the wilds of British Columbia. We see logging roads, and just a simple cut can change drainage patterns and cause debris flows and landslides. Seismic events, maybe not such a huge contributing factor to debris flows. And then dam bursts. Where's Paul? I've seen a video of where somebody breached a dam, and that caused a significant debris flow. So, okay, so triggering effects. That's climate change. So there's a nice report, the temperature and precipitation across Canada. You might have read about this. The average precipitation has increased by about 20% from 1948 to 2012. The mean temperatures increased about 3.3 in the winter and 1.5 degrees in the summer between 48 and 2016. And it's apparent that there is a direct correlation between warmer climates and precipitation. The bottom bullet I find quite fascinating, that the water retention capacity of air increases by about 7% per 1 degree of warming. And I think that's our problem. So the air is just absorbing more water than it's ever had before. So if you do a volumetric analysis of how many liters in a cubic meter of air and times it by 7%, what goes up comes down. So anyways, what is a debris flow? I'll talk about debris flows. I'll mention landslides first. Sometimes I make mistakes and I interchange them, kind of a Freudian slip. But landslides are generally composed of rock and soil, but usually do not result in a loss of life. It may take weeks or months for precipitation to percolate through the soil to instigate a landslide and to even make a detectable movement. And then debris flows, what we'll talk about today, are typically more dangerous than a mudslide or a mud flow. Debris flows, they move faster and further, and they're powerful enough to carry enormous boulders, tire trees, They're fast-moving, triggered by short, intense periods of rainfall, and can cause both property damage and loss of life. So because of this property damage and loss of life, that's what keeps me busier. And in this diagram here, this triangle, basically the 3 points of the triangle, we can have water, just fluid. We can have fine particles, like silt, coarse particles, rock and gravel. And all these move at different speeds, and they're transported in different ways. And the debris flow area that I work in is typically saturated soil or water that's carrying sediments and granular material. And it's moving typically quite quick compared to a landslide, which would be just silty material. Compared to rock falls, debris flows move less quickly, obviously. So I'll just show you a little video of a mud flow. It's sped up 10 times. A mud flow has typically lower density, so between 1,600 and 1,900 kilograms per cubic meter. They move a little more quickly. They move between 3 and 10 meters per second. Don't be alarmed by the speed of which this is flowing. It is sped up 10 times, but it's kind of neat. You can see these surges of this material coming down, moving. It's like a surge or a pulse. So this, I'll play it one more time just to kind of see this pulse action. When you compare that to a granular flow, granular flows have much higher density, up to 2,300 kilograms per cubic meter. They move a little slower. They move anywhere from 3 to 7 meters per second. And it's harder to detect that kind of surge or that pulsing. And you can just see just by the structure of it, it's much more dense. I'll play it one more time. You can see that big bouldery front. Often it's pushing a bunch of logs and charred out burnt material along the front of it. Okay, so what is a debris flow? What are the properties in a debris flow? So basically it's a gravity-driven flow of water saturated with a mixture of rock and soil and ash and organic matter and sundry debris. That's from the Swiss. I don't know why they put sun-dried debris. No. So the solid components in a debris flow range from 30 to 70%. And obviously you have to have a fairly steep channel to get these things mobilized, so the inclination of the channel is about 25 to 30%. And densities vary extremely, like you saw in that last video, between 1,600 and 2,300 kilograms per cubic meter. Velocity is everything, because in the dynamic impact equation, that's the velocity that's squared. 15 meters per second would be really ripping along. You saw in those other videos that it's more like 3 to 5. And often if I get really strange impact pressures from designers, I check their velocity first. So the volumes, we're not talking huge amounts of volumes that a barrier can stop, but in a debris flow, they can be greater than 500 cubic meters. They're channelized, so they have to flow in a channel. And we saw some of those surge behaviors or pulses. And then the front discharge is usually a little higher than the tail discharge. So everything's kind of built up at the front, and then it just tapers down until the next pulse. So that in mind, there's, with anything, something has to come from somewhere and move to somewhere else. So basically there's a start zone where debris can accumulate, or due to weathering, rainfall, snow melting, transportation, it's brought from a higher zone into this kind of transit zone. There this material can be dropped off, it can be picked up, it can be mobilized over and over. And then finally there's a deposition zone, and typically this is where the grade changes, and that bed load that's been moved from above is dropped off in a fan or in a channel down below, or it's dropped off usually due to velocity. The velocity changes, it gets slower, and the particles start to drop out of the flow. I'm not going to show a whole bunch of different examples of debris flow barriers and other solutions. There's many rigid solutions. We see them on the sea to sky, lots of concrete, heavy, solid structures. They're basically there to stop the debris but let the clear water through and retain the debris. Is anybody involved with Canmore, Cougar Creek right now? That's where there's a big they don't want to call it a dam. It's just it's a big structure to contain granular debris and let the clear water through. This is an example in Switzerland where they didn't have enough or the footprint wasn't large enough to put a large concrete dam structure in there, and they used anchors and concrete on the flanks to kind of provide some shear resistance, and then used our nets to create a face to trap the debris, almost like a giant tea strainer. This particular one is good for about 15,000 cubic meters, so it's pretty monstrous. So that's a little bit about debris flows, and I'm definitely in over my head when we get into the theory on that, but happy to share a little more about our research and our dimensioning concept. So some history and some development. The Swiss have a lot of people, and they live in a dense country. Let's see if we get the pointer going here. Laser. The idea with these early snow nets was to put defense structures in the start zone so that if you could keep the snow in place all winter long, it wouldn't mobilize and take out whatever's below it. So if you keep the snow up there all winter, then you won't have avalanches below there. So people can live safely near these avalanche chutes. So the idea in order to do that was to create kind of a roughness on the slope. And since Brugge created these nets, the nets could take the creeping snow, but because the creeping snow wants to push, and you need the net to be suspended, you need to raise the net on these posts. But if you push the snow on these nets, these posts could overturn, so that's why there's these guy wires here. So the guy wires keep the posts from moving upslope or leaning left or leaning right. The net takes the load. The posts take the forces into the ground. There's a normal force there, and then there's tension forces on these upslope ropes to keep the net from ripping out. So how did we get to where we are today? It's kind of the same principle. So we have the net, which takes the debris load. It can be from a rock fall, it can be from a shallow landslide, it can be from debris flows. The net takes the load into these posts. The posts are kept from overturning by these guy wires. You can see them there. And the posts take the normal force down into the ground. So the principle is quite similar, although the technology is much more sophisticated. So we supplied these avalanche fences. They'd go maintain them in the spring, and they'd find sometimes these avalanche nets had rocks in them, so they become sort of like quasi rockfall barriers, unintended rockfall barriers. So Geobrugge started making rockfall barriers. This is way before debris flow nets existed. And in this particular example, this is a rockfall barrier that was installed to keep rocks from bouncing down the chute and damaging something below. But due to climate change, this chute also became an area where debris was picked up and mobilized by rain, and that rockfall barrier is actually filled up with debris, and you can see the net's absolutely destroyed. A rockfall barrier is designed to take an impact in one area and stretch out. Debris flows, you have a dynamic impact over a large area and a large height, and that combination of dynamic impact pressure times surface area creates giant forces. So rockfall barriers can work for debris flow barriers, but not greatly because they're designed to do they have two different static functions. So back to these ring nets. This is not the first time that the ring nets were used in Canada. I was walking near Esquimalt, and this is Esquimalt base, Canadian maritime base, and I saw these nets on the ground and looked a little further, and then these nets were actually used, they were suspended on floats, and they were used to intercept torpedoes and submarines in World War II. Yeah, so they were worried about enemy submarines coming into Esquimalt here. And these are laying on the ground, 80 years old, near the Fiskard Lighthouse. And they'll still be laying there probably 80 years from now. So they're there. So these nets work quite well for that purpose. So first little case study. I call this the accidental solution for debris flow mitigation. And this is for a railway, which I can't name. There's only two. And they had a constant problem. This incised channel here, you can see lots of sources of debris could come down there with intense rainstorms, especially in June. In the Rockies, it mobilized a lot of this material. The only thing draining this channel was two little culverts underneath the tracks. The culverts would get filled up, and all this granular material would fill up the culverts, and it would flow either side of the tracks and then over the tracks. And railways hate losing track time, so it became kind of a maintenance issue to try to clean this out. So there's a fella here, and he's been doing rockfall for a long time, and he's bright enough to stand on the right side of the fence there. So that gentleman and this guy, and no, we didn't pick him up from the homeless shelter, but he's this is Duncan and this is Tony Morris, and these two men came up with an idea of using our barrier parts to create a strainer net. They didn't call them debris flow barriers. What did you guys call them, Duncan? They just called it doing their job. So it was great, and it was before we had official debris flow barriers. So here's those culverts. Normal flow, they can handle that. They're designed for the clear water. They're just not designed for all this granular material. And of course it backs up to the left, it backs up to the right, and there's a continuous source of debris all the way up to the Kicking Horse Highway. And there always will be. You'll never get rid of that debris. So it's a matter of how can we protect the track, keep it running, and buy us some time next time there's an event. So they came up with a plan to use the channel, both sides of the channel, put some anchors in, and basically use the guts from a rockfall barrier. So the ring nets, the support ropes, some of our brakes. The Swiss didn't even know what these guys were doing at the time. It was before my time, so I had no input. And that was installed in the autumn, and in June the next year, it already had its first impact. So it was already worth its weight. And this is, I'm not even sure, we think it's about 2005. But railways don't like to maintain stuff until they absolutely have to. So if they cleaned it out, that would have given them more storage capacity. But they didn't clean it out because that cost money. So they let it fill up. Well, there's no more storage capacity, so they ended up with washed out tracks again the next year. But they dig it out and let the water come through. And all they had to do really is disconnect the mesh and ropes on one side of the channel, pull it down, scoop in there with an excavator, haul it away, and then they're ready for the next time. I've been working 12 years with Geoberg, and I've sent out, this barrier's been hit about 6 times, and I've only sent out parts once or twice, so it's amazing. All right, so some history and development. So first we talked about our rockfall barriers. The USGS in the States kind of had a sense that our materials would work okay to form sort of a strainer, but they didn't know how the loads would work, so they designed this, looks like a giant playground slide, and they could drop debris of different compositions down it and then measure some of the forces on the barriers and see if they'd actually even work to stop this dynamic impacts. The Swiss got wind of it, and then we started doing an estimation of debris flow impacts on flexible wire rope barriers. 2005, 2008, in Ilgraben, I'll tell you a little bit more about that. We started testing barriers. We started coming up with a system that we could test over and over, one-to-one, in real impact situations. Excuse me. 2006, we thought, why don't we put a couple of barriers behind each other in in series and stop even more material, and what happens and how much material can we stop, and what are the effects if these barriers are overtopped. 2008, we came out with the first design approach proven by field tests. This was from Karina Wendler. She did her PhD thesis on this, and basically she developed a system for us, and that was her PhD work. And 2016, of course, the Europeans got involved, so they had to give it a CE mark system. So now it's a off-the-shelf flexible kit for retaining debris flows in shallow landslides system, and that makes sure that everybody's keeps honest and has a decent product that you don't mind putting your name on. 2018 to 2020, we're seeing some large-scale tests in Hong Kong. We haven't been doing any further tests since about 2016, to my knowledge. In 2020, the first practical guide for flexible debris flow barriers came out. If you want any links to these fantastic guides, if you like this stuff, just send me an email. And this is, anybody can use this. That it's really, really lovely. It takes a lot of the mystery out of coming up and specifying a system. All right, so these are our one-to-one field tests in Ilgraben from 2005 to 2008. Ilgraben is in southern Switzerland. There's a canton called Wallis. The Rhone starts up in a pass here, flows through Wallis, heads over to Lake Geneva, and then out to France from there. This is a fascinating site because they have 4 to 6 debris flows events every year. So it's a nice, reliable place to do some testing. And I just love this picture because here you can see the source area. It's about 10.5 kilometers. You can see the old fan, and because this is such a shallow inclination, like 8 to 10%, every time there was an event, it would go this way and that way and go all over the place. You can see that people really haven't resided in there. And I don't know if maybe in the 20s or so they dug a channel. So basically they channelized that to take that debris, keep it from fanning out and bringing it straight to the Rhone River. You can see it's all clear here. And then that's all bed load that's been transported down over the years. So we know the catchment area. We put rain gauges up there, and we put a bunch of geophones, different measurement devices to detect motion. And they got it to a system where we knew when it was raining up top how long or how much time it would take before we had a debris flow down below. Geophones give us sort of a sense. See, you can't have your machines or your instrumentation running all the time, right? You have to respond within a couple minutes or hours once it starts raining and get ready to start monitoring this debris flow. There's a shear wall at the bottom. It's kind of like a check dam, and then there's a debris flow balance, and that's debris flow, but I gotta change it. It's like a scale. That's Swiss for to measure. And then our test barrier is right at the very bottom, so it's easy to access. All right, so in our test setup, this is looking upstream. This is that debris flow balance, which is a check dam. In there we had different instruments for measuring impacts and weights and densities. We had video cameras going. They were all activated, lasers to measure flow height. And then because these always happen at nighttime, we had to have some floodlights. Just please, one during the day would be nice. But and then load cells. And load cells, like Duncan mentioned about our Nicolum testing, I love load cells because when you get an impact, that's the only way you know what kind of forces are on your anchors. And that helps you decide what sort of rope size to use, or maybe you need more than one rope. So I love load cells. Here's the balance. So the Swiss came up with a way to get a feel for what the dynamic impact pressure was, the density of the material, and then the flow height. And oh yeah, escape here, there we go. So let's take a look at our first, maybe not our first, but a debris net. You can see how it does that sort of straining action. These nets were never designed to stop all the debris that could come down there. We put these nets in there just to see how the impacts would affect our system. Yeah, so you'll see a few more videos. I wanted to click ahead. So the volume that went through this particular event was 15,000 cubic meters. The density, 1,600 kilograms per cubic meter, and the velocity was 3 meters per second. I'm not saying the density was the same the whole event, but it will change during the event. Kind of go from a debris flood to debris flow, if you will. Being a geek for loads in ropes, in blue, starting at 6:46 in the evening, the blue is the flow height. You can start seeing it to pick up over time. This one big spike might have been a big boulder coming through, but the flow height increased from about 50 centimeters up to about 4 meters within 3 minutes. The lower rope on the barrier is in green, so as the flow picks up, starting to impact the net, the forces start to increase till the event was over. And then the or green is, sorry, the top rope. The red is the bottom rope. So the loads on those ropes were up to 230 kilonewtons in that particular event. And of course, we didn't know what to expect, and it destroyed all our brake rings and really pushed the system to its limit. Here's another event, and if you pay attention to the right corner here, you'll see how much tension is on those ropes, and actually we're ripping out soil there. Oops. Sorry guys, deafen you with gray noise. So it doesn't look very dense, right? Like it just kind of looks muddy. But there's already a static load behind the barrier, and all that water pressure is also pushing on that debris that's there. So if your anchor's pulled out, you have a catastrophic failure. You just flip forward, and so we spend a lot of time making sure we get our anchors right. So that particular event, it doesn't seem like it could be 2,000, but maybe not from this video, but it was 2,000 measured, and the flow velocity was 3 meters per second. You can see, this is a cool graph here. In black this time, this is the flow height of the debris flow, and I don't have the height, but you can see it picking up, and then peaking, and then dropping down. And then each little bump here, that's like a surge, after the main event. You just keep on getting these pulses coming through. And for fun, we'll look at the force in the red rope. It starts at 0. There's not much pressure on the net. There's not much tension on the wire rope. It starts to increase as the flow height increases. Once the flow height reaches its peak, the forces also reach its peak, and then the load actually dropped back down. So we went from a dynamic impact case to more of a static loading. Dynamic impact always has a higher result on the barrier than the static case. And this is a little video just to show what overtopping is. So again, this barrier wasn't designed to stop everything. We just wanted to see how well they perform if they get absolutely, I don't want to say obliterated, it wasn't obliterated, but it's, this, when I see this video, this is what really scares me about debris flow, so I take it really seriously when we put them in, because this is what can happen. Picture truckloads of concrete coming down at 3 to 5 meters per second. It's not that dense, but it's, what's concrete, 28? This is 23, 21 kilonewtons per cubic meter. Yeah, scary stuff. All right. Let me get my... So we did full-scale tests in Ilgraben, and Karina did a bunch of laboratory tests, different water solid content ratios. In this particular test, it was 45% water, 55% solids. The net opening was 3 centimeters, and basically we wanted to try to calibrate impact pressures with tensions and come up so we could calibrate our software. And it's a very similar graph. There's no load on the ropes until that dynamic impact comes. As the debris is filling that net face, those forces keep on getting greater and greater. After the event, the dynamic impact effect is gone, you're down to the static load condition, and that worked pretty good in our models. And we did some testing with multiple barriers to see if there would be like some velocity changes, or how much material do they store, what's the angle of material behind the barrier. So combining our field tests with our lab tests and numerical modeling, we were able to come up with a program to help us design nets for all sorts of different applications and impact pressures. So for those of you who are interested in pressures, so normally if you have earth pressure, it's just basically the density of your earth times some sort of passive or active earth pressure value times the height. So it's triangular. But in debris flows, we assume in that first surge that comes that the dynamic impact pressure in the top of the surge and in the bottom of the surge, they're the same. So it's like a squared loading. So you get this dynamic impact in a rectangular loading, and as soon as you get that, you also have a static result of it. But then the next surge comes, and the surge is probably the same dynamic impact. So it kind of crawls over the first layer, and the static pressure starts to develop, but the dynamic impact pressure is still the same. So this can do this 10 times. You can assume 10 surges. Typically, we assume 3 to 5 for our barriers. Once the barrier is filled, if it's overtopped, there's sort of a drag force. So if the overtop, you take the height of the overflow height, and there's a bit of a drag force which results in some additional loading of the net itself from the friction of the material rolling over top of it. So we can take that into account. And by modeling this, we can choose barriers of different heights, different widths. And if we have the surface area and the height and the dynamic impact and the number of surges, we can calculate what the forces are in the ropes, which helps you as designers determine how long the anchors you need to put in the field. So our upper ropes from simulation were, on one particular model, were 170 kilonewtons per anchor, and when we measured it in the field, it was about 150. So we've got a bit of a conservative, a little bit of a conservative factor for modeling stuff. It's just we can't test every single barrier. We have to have good legs to stand on, though, when people come to us for a site-specific one. So on top of all that, again, the practical guide for debris flow and hill slope debris flow protection nets. These are great guidelines and books, and fairly easy to understand, and I find them interesting. Maybe not everybody does, but so because of this, we have 2 systems now that are off the shelf, you can say. So when people ask me about debris flow barriers, I can say, do you want a Tacoma or a Tundra or Sienna? F-150, I have a truck for all applications. So standard debris flow barriers, the VX system, they're designed for V-shaped channels. And I'll get the pointer going because I lost that again somehow. So kind of a V. There's no posts required. They're for narrower channels. Standard ones are 15 meters, but we will push it, that's for sure. The impact pressure is between 60 and 120 kilonewtons per square meter. And what's really important with debris flow barriers is that you leave an opening underneath here, because if your bottom rope is on the bottom of the channel, you're going to stop absolutely everything, and then you've got maintenance issues, right? So you want to let what normally comes down year after year through, and then when you do get that event, that's when you want it to start trapping material. You don't want these things to become a maintenance issue. If you have wider channels, 25 up to 25 meters and wider, in a more U-shaped, then we require posts to help keep the net height up, and also to take some of that load from the impact pressure on the net down into the ground. So these posts have these guy wires with anchors in the channel, and they're rated up to 180 kilonewtons per square meter. And every situation is different. It all depends on the loads that we're anticipating and the ground we're anchoring into. Problem with posts, it's hard to put posts in a channel. When you get all the environmental restrictions and things like that, sometimes it can be tricky. Luckily, all the ones I've got in Canada, where we've had to put posts, they weren't fish-bearing streams, they're often just dry channels. All right, so the Swiss like to come over and see what the Canadians are doing. So this is Gabriel. He's one of our new technical guys in Switzerland, and I like to show him. We've got some pretty cool projects in Canada. This is for a railway I can't mention, but one of the two, and a beautiful installation. So I was showing him the different parts. So the barriers have ropes. So the mesh takes the load, transfers it into the ropes take the load, transfer it into the ground. And then we've got these brake rings. I can pass them around if anybody's curious. See these up close. The brakes, no, those aren't brakes, that's a Rocco ring. Brakes would be too heavy to lift around like that. The Rocco rings, that's what we make our nets out of. And they can be a wrap of 7 wraps or 19, or the more wraps that we have in that ring, the stronger it is. So that does the bulk of the surface area. And then brake rings, these brake rings, they're designed, you can see these steel tubes with aluminum sleeves on them. We feed ropes through these tubes, and then when they're under tension, they deform. And when these brakes, when they deform, that takes time, and it creates distance. And if we have time and distance, then we are reducing the impact forces on our anchors. So those are brake rings. And then these are abrasion plates. So if the barrier were to be overtopped, one of the problems is these debris flows, if it's super granular and dense and moving quickly, it can actually cut the wire rope. So these plates protect the wire rope so that the system can stay standing. And then, of course, we've got some posts there to hold the mesh up high. So another little video here. Here in this video on the right, you'll see kind of the 3 steps. You'll see debris flowing underneath, normal flow, and then as the flow increases, we're starting to stop material, we're starting to fill, and then we've got an overflow scenario. Sorry about that. As soon as it starts stopping material, that's when the impact pressures are coming on and the anchors are loaded. Continues to fill. So that's that second load case, and then this would be that third load case. All right, so when we're dealing with debris flow barriers that are really wide areas with high impact pressures, we need to put posts in there. And I'll show you more post foundation pictures, but the post foundation has to be strong enough to resist that impact pressure. You don't want to shear it off the bottom of the riverbed. So typically they have 2 heel anchors. Let me get a laser pointer here. So this is cross section. There's 2 heel anchors in tension, and then there's 1 micropile in compression, and they're all cast into about a cubic meter box. And the actual anchors that bolt your post down, they're set in the wet concrete. They're a thread bar, like number 10 bar. And they're not connected to the actual ground anchor. So basically, the ground anchors keep the concrete block from moving, and then these green anchors, these stubs, they prevent the post base from shearing or getting pulled out. To terminate these anchors, we put plates and nuts in there to increase the surface area for resisting it getting pulled out of the concrete. And of course, there's some steel in there too to armor it. I've been getting more phone calls about driftwood barriers, which is really bizarre. And it's just like after all these wildfires, they're not worried so much about a bunch of sediment or debris coming down. They're worried about a bunch of half-burnt logs that are laying in a gully. And they know there's a culvert downstream, and they know as soon as a log breaches that culvert opening, it's going to plug up that culvert, and then you get a flow over top of it, and all of a sudden that culvert has become a dam. You see that a lot. And the debris flow modeling for woody debris is different. The impact forces are way less. We actually just use a hydrostatic design approach to that. We don't use the denser granular material. But definitely something to keep in mind if you're interested. And this is Cougar Corner. That's the Trans-Canada Highway. And another railway down below. And a few years ago, we supplied a bunch of snow nets. This is in Glacier National Park. And we just could not get our standard snow nets to fit in these kind of incised gullies. So we used debris flow barriers, and they're really robust and tough, and they were a great solution for holding snow in place. So there's Rogers Pass, if you look up, there's 3 of them up there. We flew them all in with a helicopter. It's crazy. So a lot of people say, well, how do you clean these out? And have to be a bit careful. Once they're loaded up, especially right after the event, there's quite a bit of static pressure in there. You've got saturated debris in there. But over time, the water table will start to drop. And because the nets are connected with wire rope clips and shackles, you can undo some shackles, you can take a gas axe and start cutting some of the wire ropes, and all you need to do is open up a little bit of that net and start digging in there with an excavator bucket, and then you can just keep on pulling up the material. And Presti, did you have any debris cleanouts in California that you had to do. Yeah. Yeah, Presti's, some of these slides you'll recognize, he worked for Kane Geotech, and I do a lot of work with Kane more for attenuator stuff, but Bill Kane's probably, I don't know, 30 debris flow barriers or something like that. They're all in post-wildfire areas. Yeah, so lots and lots of cleanouts. The trick with them is to dimension your anchors so that you can reuse them. To put anchors in, that's the most expensive part of your system. So it doesn't matter if your mesh gets destroyed or gets damaged, you can still use your anchors again. How are we for time? I'm at 40? Whew. Sorry, okay, I'll talk faster. 40, another 10? Okay. All right, systems and case studies. So post-wildfire debris flow barriers in the USA. So I stole some of these from Bill. Burn vegetation creates a waxy coating on the soil, increasing rainfall runoff. Hydrophobic soil more than doubles the rate that water will run off into water courses. So if the water is running off twice as fast as it used to, and your intensities are greater, and your frequencies are greater, all those are the perfect storm to create debris flows. So what do we do if we want to put in a barrier at a location where we might have a potential debris flow after a wildfire? So there's kind of 5 steps. So first we got to do a geohazard assessment. Will this particular area, will it pop if there's a big rainstorm? Will it flood? We need to look at, how much debris can come down. Where is it coming from? Can we put a barrier in at this location? Phase 3, this is the hardest part of all. This is environmental permitting. You could send a person to Mars more quickly sometimes than get a debris net in, although this is protecting people and things. Phase 4, the engineer design and specifications. This is where I kind of come in and I give you the anchor loads, and I give you the drawings, and I help with your foundations, and help with pricing and forces and all that stuff. And then the very last phase, which is most fun for me, is actually constructing these things. So, you got to look at a site, and the site should be chosen on is this channelized? You can't put a debris flow barrier unless you have some channels to anchor into. Can you anchor into the ground? There's a lot of crummy ground conditions out there. We can't put anchors in. Where we put a net, is there enough room behind the net to store debris? What are we protecting? Like, is it worth putting something in there? So, a few things to consider. Sometimes you'll see images like this. It's like, well, I don't know where to put a debris flow barrier. So one little trick is put them where you can. so obviously we don't want to put debris flow barriers all over this place, but if you put them in areas close to where they come out, they've got good access, you want to be able to clean them out. And if you, rather than putting a debris flow barrier across this whole stream, which might be too big, you can put them in just kind of little spot treatment areas. And what's cool about them, one area might pop and the other one might not, but if they all pop together, that creates a big problem downhill. So if you put 1 or 2 above, that might be enough just to buy you some time before they're hit, and then that relieves all this debris flow issues below here. We have a really cool tool. I won't get into this, but if you're interested in debris flows, the hardest thing I find for people to calculate is that dynamic impact pressure. All of us here would have a different opinion, whether it's 112 kPa or 160. We all have different opinions about velocity. It comes with experience, but we've got this great tool that helps you come up with velocities, with impact pressures, storage volume, and it's all based on geometry and different parameters that you pick to model. A quick little debris flow barrier study in Montecito. This is in Santa Barbara County. And Presty, were you involved in any of this, or did you come before your time? Okay, yeah, 2018. That was back in the old days there. In 2018, Montecito debris flows in Santa Barbara County were a result of intense rains in areas affected by the Thomas wildfire in 2017. So I think the fire stopped burning in December 2017. January 2018 and intense rains. And this is kind of like where all the mucky mucks live, like movie stars and Oprah. So 21 fatalities, 100 homes destroyed, 300 other homes were damaged. Highway 101 was shut down. I don't think they don't like highways down there anymore. California Geological Survey scientists estimated that the monocytic debris flows had speeds of 10 to 15 miles per hour. So I put it in metric because I don't know how fast it is, but 4.5 to 7 meters per second. So that makes sense. That kind of lines up with the traditional velocities. And this was capable of carrying boulders as large as a tow truck. So it's pretty. There we go. So this is interesting. Back to those woody debris flow barriers. They had giant culverts there. They were used to flooding, but not to the degree after a fire went through there. So all you see that first front that came through was just woody debris laying in the channel. That was all pushed through by the boulders and debris that came after. You can see things were moving along fairly good. You can see some splash zones up here, but not super fast. If these boulders were moving really fast, they would have ripped out a 2x4 house in no time. They put in a ton of debris flow barriers. The only way they could get them in was to call them temporarily, because you can't put permanent solutions in water areas like this. Some environmental people, they call these gill nets for bears, because they're round rings. Like, there's a lot of resistance, But anyways, Bill overcame that, and they all got together and they built. So now, how can we call that temporary? The hazard. We still have a chance of debris flows. Well, over time, that area that burnt out will green up again. So if there are intense rains in the future, maybe nature will be back to the way it was. Maybe not. But being temporary structures, that was the only way they could get them in. I encourage them to maybe just do like a 5-year renewal, buy you some more time, let things grow up. So this is a little case study near Tank Hill. This is a debris sedimentation area, or like where the debris in a flow could settle. But you can see how small the drainage culverts were. What happened was here, debris flow happened, it filled up the sediment pond area. It flowed over the top and it created flooding on the tracks as well as on the highway below. So what they were worried about, the railway did not have enough time or money to build a clear span structure to let everything flow underneath. And even if they did let it flow underneath, it would take out the highway. So they decided on a debris flow net. So I checked out a bunch of sites with them, and this one was just an absolute beauty. Nice channelized area. Not super active, no salmon in here. This is a natural pinch point, and behind there's like a giant basin where we could store debris. So we measured it all out. We came up with a system about 27 meters wide and about 5 meters tall, and at the base about 6 meters, so it fit all our requirements quite easily. I measured it out and I ordered the system for the client, and then in the meantime we went back and kind of using rudimentary tools. You can see string lines. We literally pulled strings across so we could mark out where every single anchor was. We knew where the posts were. There's green marks for the posts. You can see the green line of the barrier, and it's amazing what you can do with a string. The batteries never die with a string, so it's they're not good in the wind though. That's what I found. So the contractor mobilized. This picture was in March. It's quite dry. No, February. March, you can see it. The creek is already starting to flow. The way they managed the water here was to over-excavate the stream channel, put some big culverts in there, fill material back onto the culverts, and that gave them a nice flat level pad to work off of. It also brought the water level down, and the whole plan was to move those culverts out when they were done. So excavator came in, moved things around for us. The drills came in. One side of that channel had nice bedrock we could drill in. The other side was more fluvial material. We had to use wire rope anchors in the rock, and we used self-drillers in the soil, which is always tricky. Of course, testing. We got to take this stuff serious. There's big loads on there. So here we are, some testing and some dunnage, checking the jack, checking the time, loading it up in increments. Rockfall barriers, I don't worry about testing them for hours or minutes because the impact is boom. It's quite quick. Debris flow nets, they get hit. And you saw when they're filled up, even when they're done being hit, they still got a static load on them. So those anchors are still under tension. Our materials started coming in. Are we at 50 yet? Okay, we're going to get her done in 51. So everything's quite light. You can pack it in. Excavator brought in the nets. They built the rebar cage. They put those tension anchors and formed it nicely. Put the plates on. Removed the culvert. Installed the posts. Put the mesh up. And I thought this fellow might be here tonight, but he's not. I won't tell who his name is, but good fella. And then we basically signed it off. Was a very successful project. This is Cougar Creek in Canmore. It's 40 meters wide and 6 meters tall. A very special installation. No longer in use. It was designed to trap about 1 million cubic meters. There's a potential of 10 million. So there's a large dam being built up above here to contain that debris. And then Mr. Wilson knows this one. You remember that day? He showed me a picture. Do you think you can get a net in here? And I'm like, I think so, Paul. I think we could. He was like, really? So yeah. This turned out to be one of the most beautiful projects. There wasn't even a change order on this one. Like, it was just everybody worked together with beautiful granite. And this is near Britannia Creek. If you want to see us personally, I can tell you where it is. So key takeaways, and then I'll stop blabbing. On here, flexible debris flow nets. They're an effective tool to mitigate post-wildfire debris flow events. The whole process is quick. After fire events, it's a fully tested, certified system. We've got design tools to help you, and they can be an environmentally conscious construction, less concrete, less steel. Can be temporary, small footprint, and they do allow fish and wildlife to pass under the nets. Thank you, and any questions?